So make sure that you know what atmospheric pressure is and what standard atmospheric pressure is. 1 atmosphere is 101.3 kilopascals, and standard temperature and pressure is 0 Celsius and 101.3 kilopascals. Don't forget that 0 degrees Celsius is 273 Kelvin, or actually 273.15 Kelvin, and 100 degrees Celsius is 373.15 Kelvin. Kelvin is an absolute temperature scale, goes down to 0 Kelvin, which means that there's no energy available. So Celsius and Fahrenheit are more arbitrary, so we say degrees Celsius. We don't say degrees Kelvin, we just say 2 Kelvin. The average temperature of the universe is actually about 2 Kelvin, 2 to 4 Kelvin. And you have to know what temperature is relative to kinetic energy. Don't forget average kinetic energy and the relationship with temperature. What is temperature? Look that up. So we measure pressure with a barometer. We measure temperature with a thermometer. Okay. We need to know what happens to matter when I increase its temperature. So I'm increasing the kinetic energy of matter. What's happening to the temperature? Okay, so the relationship between heat added and kinetic energy has to be considered. Now, let's talk about some phase changes. When I heat water, let's say I heat water from negative 20 degrees Celsius to 120 degrees Celsius. Let's examine what happens. Well, as I heat the water from the ice from negative 20 degrees Celsius, it's going to gradually warm. So as I heat it, the temperature is going to rise 19, 18, 17, 16, 15, 14, etc. When it gets to 0 degrees Celsius, the temperature stops rising. I'm still adding heat, but there's no change in temperature. But something's happening. The ice is melting. That's a phase change. But I'm adding heat, but it's weird. I'm adding heat, but there's no temperature change. That's because there is an increase in the potential energy. The average distance between the water molecules is increasing. So I'm adding potential energy, so I'm not adding kinetic energy. So where's the heat going? I'm adding heat, but there's no temperature change. I'm adding heat, there's no kinetic energy change. It's going into an increase in potential energy. So then all the ice melts and I get to 0 degrees Celsius, all liquid. And then what happens is I add heat and the kinetic energy increases, the temperature increases, and it goes up to 100 degrees Celsius water. And then what happens is I add heat and there's no temperature change. It levels off. Again, I'm adding heat, but there's no temperature change. I'm adding heat, there's no increase in kinetic energy because that's a phase change. A phase change, you add heat, but there's an increase in potential energy. So the energy is being absorbed, but as potential energy. And then when it's all changed to steam, when it's all changed to a gas at 100 degrees, all steam, then the temperature starts to rise again. So a phase change is when you have an increase in potential energy without a temperature change. It's not an increase in kinetic energy, it's an increase solely in potential energy when you have a change of phase. Okay. Now, there are two phases of matter that can flow. We're not talking about plasma, but yes, plasma can flow. But we're talking about solid, liquid, and gas. And the two phases that can flow are going to be gases and liquids. So when you study gases and liquids are called fluids. And the study of fluids is called fluid dynamics when the fluid is moving, or fluid statics when the fluid is not moving. So a fluid is something that can flow. Fluids are gases and liquids. Remember that evaporation is a cooling process. When you sweat as a person, your temperature will decrease as the sweat evaporates. When you have a beaker of boiling water and the gas is evaporating, it's actually cooling off the water. So the concept of evaporation is known as a cooling process. Condensation, when condensation forms in clouds, when waters form through the process of condensation, then that's a heating process. So it goes from a gas to a liquid. Where's the energy going? Well, it's going into the surroundings. So when condensation occurs in clouds, then that is a heating process. So evaporation is a cooling process. Condensation is a heating process. So when water evaporates, you're taking that amount of higher kinetic energy out of the liquid, and you're left with, on average, lower kinetic energy material, so it's going to be cooler. Equilibrium. If I have a closed container, and in that closed container, it has a constant temperature. What's going to happen to the rate of evaporation relative to the rate of condensation? Well, at equilibrium, the rates will be the same. You know, when it reaches equilibrium, that means that the evaporation and the condensation are occurring at the same rate. Especially, it's most easily demonstrated in a closed container at a constant temperature. Make sure that you understand the ideal gas equation. Let's talk about that for a second. Write this down. PV equals nRT. So you'll notice when things are at the same side of the equation, for instance, P and V, they would be indirect because they're on the same side of the equation. So as one goes up, the other goes down. So as I increase the pressure of a gas, I'm going to decrease the volume. As I decrease the pressure, I'm going to increase the volume. Whereas pressure and temperature are on different sides of the equation, so as to demonstrate that they are directly related. As I increase the pressure, I'm going to increase the temperature. As I increase the temperature on a gas, I'm going to increase its volume. For instance, if I take a balloon, I put it in an oven, I turn up the temperature, and it's going to expand. As I turn the temperature way down, it will contract. It will become less volume. The relationship between moles and pressure, they're on different sides of the equation, so they are direct. There's a little bit of a trick. Let's say I have 1 mole of a gas, right? And I add 2 moles. Because you started with 1 mole and you added 2 moles, what's going to be the change in pressure? It's not going to double. It's going to triple. If I have 1 mole and I add to it 3 moles, then the pressure will change 4 times. If I have 1 mole of a gas and I add 4 moles of a gas, the pressure is going to increase 5 times, because it's the total number of moles that you end up with, because you're starting with 1 mole of a gas. Understood? Okay, so make sure that you understand the relationship among pressure, volume, moles, and temperature. I think many months ago at this point, I wrote a chart on the board and we discussed that. So you want to pull out those notes and see if you can add that to your review sheet. Hydrogen bonding. Hydrogen bonding literally is the answer to so many questions. Why does water have such a low vapor pressure? Right? Because the water is held together, it doesn't evaporate easily, by hydrogen bonding. Hydrogen bonding explains surface tension. It explains high heat of fusion when you melt ice. It explains very high heat of vaporization when you change water from a liquid to a gas. So it really explains a lot of the thermal qualities of water, the hydrogen bonding. Let's talk about boiling for a second. Boiling is that temperature at which water achieves a vapor pressure equal to the atmospheric pressure. If I reduce the atmospheric pressure by climbing up a mountain, then water will boil at a lower temperature because the vapor pressure doesn't have to be as great. So it will boil at a lower temperature. Let's say I have a pressure cooker. Your mom or dad may have a pressure cooker at home that they use to cook food. And the way that works is I increase the pressure inside the pressure cooker, I will increase the temperature of the boiling water. Water may boil at 110, 120 degrees, not at 0, because you're increasing the pressure inside the chamber, and you are increasing the atmospheric pressure, so to speak. So the water will need to boil at a higher temperature because the vapor pressure has to go much higher, because you are increasing the atmospheric pressure inside the pressure cooker. So maybe look up pressure cooker, look up the relationship between increased vapor pressure because of increased atmospheric pressure. For instance, if I go down in a submarine and I'm down really low and very high pressure, the water is going to boil at a higher temperature because the pressure is higher. Every 10 meters of water, approximately, you get an increased atmosphere. You go down, 100 meters, that's 10 atmospheres. That's a tremendous amount of extra pressure. So the water will boil at a very high pressure. Okay, not that you're in a submarine and it's going to be 10 atmospheres of pressure. So anyway, so look up PV equals nRT and the relationship among pressure, volume, moles, and temperature. Look up hydrogen bonding. Look up the relationship between vapor pressure and boiling. How going up a mountain you're decreasing the atmospheric pressure, you're going to decrease the vapor pressure, decrease the boiling point. The opposite is true if you go down into the ocean or you use a pressure cooker on top of your stove. So look up those values as well. Let's talk about certain forces that exist between molecules. Dispersion forces, ionic attractions, hydrogen bonding, London forces, van der Waals forces, So even though hydrogen bonding is the answer to everything, one thing it is very important to consider is how hydrogen bonding works in water and how that will aid in the solubility of materials. But there are certain forces at work, like in terms of attractive forces, like dispersion forces, London forces, van der Waals forces, hydrogen bonding, ionic attractions, and these are very important to consider, and you should look those up. Let's talk a little bit about hydrogen bonding. Hydrogen bonding occurs in water, but it can occur between hydrogen and any electronegative element, not just oxygen. But that's predominantly what we talk about because water is made of hydrogen and oxygen. Hydrogen bonding, you talk about hydrogen bonding when you're talking about the solvation process. So there you have ionic or ionic bonded materials with ionic attractions playing a major role with hydrogen bonding. So ionic solids are easy to dissolve in water than non-ionic substances. Let me explain. When you're talking about solubility, really there's two major elements to it. There's temperature of the solvent, and there is the nature of the solute. The nature of the solute. So even though covalent bonding and ionic bonding is from the distant past, that's semester one, it still comes in very importantly with the discussion of solubility. What's the significance? Well, covalently bonded atoms, generally we talk about gases, carbon dioxide, hydrogen gas, oxygen gas. Those substances are better dissolved in cold solvents. So covalently bound material, methane for instance, that's very covalent. A lot of substances that are covalently bound, many of them are gases at room temperature. So they are more soluble in cold solvents. Ammonia is the most soluble of all the gases. So the nature of the solutes, is it covalent bonding or ionic bonding? Covalent bonding, a rule of thumb you could say, is that those substances are more soluble in cold solvents, and the solids, the ionic bonded solids, are more soluble in warm solvents. The greater the temperature, the more soluble the material. Now, what dissolves the material? Well, hydrogen bonding will, essentially. So, especially with the solvation process, sodium chloride will break into sodium ions and chlorine ions, and the water molecule, because it's polar, will surround each of those and line up relative to the charge. So you have to know the structure of the water molecule and how hydrogen bonding plays a role. So you have to know what the electronegativity differences between hydrogen and oxygen are doing to the molecule and why you have these slight charges. You have a slight charge at the oxygen is a slight negative charge. You have a slight charge at the hydrogen. It's a slight positive charge, and at the other hydrogen as well. So electronegativities are going to become very important. Ionic attractions are very important. Hydrogen bonding is going to be very important. Dispersion forces are going to be very important. The nature of the solute, covalent bonding, ionic bonding. Remember, I could draw a distinction with solid solutes. If it's made of a group 1 salt, sodium chloride, sodium iodide, sodium carbonate, sodium acetate. Those group 1 compounds, sodium, lithium, potassium, rubidium, cesium, francium, those group 1 metals, when they make a salt, they're generally all soluble. For instance, calcium carbonate, group 2. Calcium carbonate, very insoluble. Thank God, because the crab shells, the clam shells, the arthropod shells, they would all dissolve in the water. That wouldn't be a good way to make an exoskeleton. But sodium carbonate is very soluble, very soluble. Magnesium hydroxide, not particularly soluble. It's a group 2 salt. Group 2, well, it's a base, fair enough. Magnesium hydroxide, not very soluble. Sodium hydroxide, very, very soluble. So you could say as a rule of thumb that all group 1 metals, when they make a salt, they're all soluble. So let's review. Solute or solubility depends on the temperature of the solvent and the nature of the solute. When you're talking about the nature of the solute, you're talking about what kind of bonding is there, covalent bonding, ionic bonding, dispersion forces, hydrogen bonding, ionic attractions, electronegativity, the structure of the water molecule, the polar nature of it. You're talking about a gas versus a solid. Gases are more soluble in cold solvents. Solids are more soluble in warm or hot solvents. Okay? So that's pretty much a good review of aqueous systems as a lead up to solubility. Look up some very basic solubility problems. Like if I said to you, the solubility of sodium chloride at 40 degrees Celsius is 42 grams per 100 grams of solvent. So at 40 degrees Celsius, sodium chloride, I'm saying, just as an example, it's not true numbers, I'm making these up, I can put 42 grams of sodium chloride in 100 grams of water at 40 degrees Celsius. Okay, fine. So, this is the question. How many grams of sodium chloride will fit into 300 grams of water at 40 degrees Celsius? Well, you know your solubility at 100, so it's a proportional relationship. So it'd be 42 times 300 divided by 100, or just simply, well, what did I do to 100 to get 300? I multiplied it by 3. So 42 times 3 would be 126. So I could put in 126 grams of sodium chloride into 300 grams of water. So you want to know how to do very basic solubility problems. The next section we're going to talk about molarity, molality, and how to do calculations with those concepts. Okay, there's going to be some calculation problems. There'll still be multiple choice. And you may want to, if you're weak at the problems, you may want to skip those and go back if you have time. But like, for instance, I'll give you some examples and you can ask me in class. I'll just make up some problems right now that are similar to the problems that are on your final. All right, here it is. Here's one right here. What is the molarity of 400 milliliters of solution in which 3 moles of sodium iodide is dissolved? Next, what mass of sodium carbonate is needed to make 3 liters of a 1 molar solution? All right, next. How many milliliters of a 3 molar sodium bromide solution are needed to make 350 milliliters of 0.75 molar sodium bromide? You'll have to do specific problems relative to molality. Molality is the moles per 1 kilogram. You'll have to do problems for freezing point depression and boiling point elevation. Remember, the equations are similar. Delta T equals N Km. Delta T equals N, which is the number of ions, times K, which is the constant. Is it the freezing constant or the boiling constant? And then M is the molality. If it's water, like glucose, N would be 1. If it's sodium chloride, N would be 2. If it's calcium chloride, CaCl2, N would be 3. So you'll have to be able to do problems with boiling point and freezing point elevation. You'll have to do problems with acids and bases. So you're going to have to know some of your formulas. Make sure you know the formula for instance, phosphoric acid. You have to know what a Lewis acid is. You have to know what a Brownstedt-Lowry acid or base is. You have to understand what Arrhenius acids and bases are. And so the different theories, the Arrhenius, the Brownstedt-Lowry, and the Lewis, will become important. You have to be able to calculate pH. pH is the negative log of the H ion concentration. You have to understand characteristics of strong acids and bases. You have to understand what acid dissociation is. And just because something is an acid and dissociates doesn't mean it dissociates well. HCl, H2SO4, they dissociate very well. But something like acetic acid doesn't dissociate very much. And that would be referenced by your dissociation constant, your Ka or your Kb. So that determines whether or not it's a strong acid or a strong base or a weak acid or a weak base. Look at the Ka, dissociation constants. Okay. You have to understand things about acetic acid. If I put acetic acid in water, I want to know what the equation is for its dissociation. And then I want to know what happens to the acetate ion. Is it what kind of species is it? You're going to have to do problems. I gave you a review packet of problems that were right off the test on acids and bases. Do those. That's a separate video. So make sure you can do those problems. The Ka for acetic acid is 1.8 times 10 to the negative fifth. That means that the dissociation constant is very small. That means it would be a weak acid. So understand what your Ka and Kb mean. I think I'm repeating myself a little bit. That's okay. Redox. Make sure you know what is oxidized and what is reduced. You want to be able to write the half reaction for oxidation, the half reaction for reduction. You want to be able to look at a chemical equation and be able to put in all of the little oxidation numbers. And you want to be able to say, well, this is a oxidizing agent, or this is a reducing agent. If, let's say, you have sodium sodium plus water yields sodium chloride plus hydrogen gas. So the hydrogen in the water, the plus one, is clearly being reduced. The sodium is being oxidized. It's going from 0 to sodium chloride plus 1. So the sodium is being oxidized. It's giving up electrons. So it is the reducing agent. The hydrogen is taking those electrons. So that's the hydrogen is the oxidizing agent. So you have to be able to determine which is which. Let's say I give you an equation. Sodium plus oxygen yields sodium oxide. You have to be able to tell me, like that, what's the reducing agent, what's the oxidizing agent. So oxidizing agents and reducing agents are very, very important with this test. You will have to tell me what charges exist in any particle. For instance, if I say sulfur trioxide, you have to say that the oxygen is -2 and the sulfur is +6. If I say sulfate, well, the oxygen is -8, there's 4 of them, so the sulfur would be +6 because the whole charge must be -2. So if I say nitrate, so the oxygen is -6, the nitrogen must be +5 because the overall charge is -1. So given any substance, you have to be able to tell me what is the charge of each representative element in the formula. No doubt about it. If I give you an equation, I'll give you one. Lead nitrate plus sodium iodide yields lead iodide plus sodium nitrate. You got to be able to tell me what is the oxidation number for each element in that formula and whether or not there's a change. Is there a decrease in an oxidation number or an increase? If I say to you calcium plus water yields calcium hydroxide plus hydrogen gas, you have to tell me that calcium is 0 plus water, that's +1 -2 for the H2O, and then you'll have to say that calcium is going to be +2, then the calcium hydroxide, that would be -2 +1 for the oxygen and hydrogen and hydroxide, and then you'll have to say that hydrogen is 0. All right, so you have to be able to do that. You have to be able to tell me what is the oxidation number of everything involved. Okay. You have to be able to recognize reduction half reactions, oxidation half reactions. You have to be able to tell me what element is most easily oxidized. Lithium is very easily oxidized. What does that mean? Well, lithium will want to react. So lithium goes to lithium +1 state very quickly because it wants to be reacted. In other words, if I said lithium plus water, I would end up with lithium hydroxide like that. It would kick out the hydrogen because it's much more reactive than hydrogen. If I said lithium plus iron chloride, you'd get lithium chloride plus iron because lithium is easily oxidized. So you have to be able to tell me, that a metal is generally oxidized, with the exception of, some of you got that wrong on the test, mercury can be reduced. That's very important. And let's see. Now we want to talk about, here, I'll give you one here. Identify the pair of metals that lists the more easily oxidized metal on the left. I'm not going to tell you what metals there are. The first electrochemical cell was invented by blank. That's one. You want to talk about what's a voltaic reaction. That's a chemical reaction that produces electric current. Electrochemical cell or electrolytic cell is one that uses electric current to come up with a chemical change. You have to know anode and cathode, plus or minus for voltaic and electrolytic cells. You have to know what a dry cell is. What's the electrolyte? It's that gooey paste. Why is a alkaline battery, why does it last longer than a regular dry cell? You want to know about the standard potential, the half cell potential for hydrogen is 0. And you're going to have to determine the E naught cell given an equation. And that's about it. Not much more. The electrolysis of water is an electrolytic reaction where I'm using electricity to separate water into hydrogen and oxygen. That is non-spontaneous. So if any chemical reaction is non-spontaneous, I can make it happen using electricity. Okay, that's it. Ask me questions. You have many days still before your test, before your final exam. You have a week. Don't forget, by Friday, I want your review sheets. Okay. Have a good day. All the best. Thank you, and goodbye.